Well, good afternoon, ladies and gentlemen. So today we're going to move away from closed systems, entropy balance. We've actually done a lot with closed systems so far. We've done the various forms of the entropy balance. We've done the property relationships, which are applicable to all systems, not just closed systems. We've done isentropic processes. Again, this is applicable to all systems, not just closed systems, but we've done a lot of material so far, starting with and applying what we know to closed system entropy balance. Now we're going to move on to open system. How entropy flows in and out of open systems, how entropy is generated in open system devices. So we're going to move on to open system application of the energy balance today. And as you might vaguely recall, we have a device or we have a process or a machine or a function for transforming closed system conservation relationships into open system conservation relationships, the Reynolds transport theorem. We're going to be applying the Reynolds transport theorem to a closed system entropy balance to arrive at an open system entropy balance for entropy, as I said. And then we'll do an example. We'll apply our open system entropy balance and look at entropy generation within a nozzle. So we're going to look at a nozzle. We've done a lot of stuff involving nozzles, turbines, compressors for the energy balance. We're going to start doing a few things very soon for the entropy balance for open system devices. So one example today for an open system device, for an entropy balance, and derivation of the open system entropy balance. That's the plan for today. So let's write down the Reynolds transport theorem one more time. Remember beta here. Beta is some extensive property. And lowercase b is the intensive property, so beta per unit mass, or the intensive property. So we've got the extensive and the intensive property, beta and lowercase b. So the Reynolds transport theorem says that the rate of change of beta within the closed system is equal to the rate of change of beta within the open system plus the outflow of beta due to all the mass interactions minus the inflow of beta due to all the mass interactions. So we derived the Reynolds transport theorem several weeks ago when we were going from closed to open system energy balances. So now we're going to apply the Reynolds transport theorem to entropy as well as energy. To do that, let me remind you here with the closed system rate base. So this is a rate here. This is beta dot within the closed system. This is beta dot within the open system control volume. So we're going to be looking at the rate-based version of the entropy balance for a closed system and using the Reynolds transport theorem to derive the open system equivalent. So here we have the closed system here receiving various heat interactions. So we have Q dot T interaction. So you put a thermometer right here, and that's your interaction temperature right there where the heat flow crosses the system boundary. Q dot over T interaction is your entropy flow into the system. And we have multiple heat transfers. There could be many heat transfers with many temperatures here at the system boundary where the heat crosses into the system. And that all results during some process over a rate of change in entropy within the system. And of course, there may be some entropy generation in the system due to the presence of some sort of irreversibilities. So the rate, so the S balance on a rate basis for a closed system is S dot, or if you like, ds dt in my closed system is equal to the sum of Q dot over T interaction over all heat transfers plus S dot gen. So this is rate-based closed system S balance. So S dot within my closed system, or ds dt within my closed system, is equal to the sum of all entropy transfers due to heat interactions plus any entropy generation within the system due to irreversibilities. That's what the S dot gen is about. So S transfer due to heat transfer, and then we have S generated due to irreversibility. That's what the last term is about. Now, in the case of entropy then, for our closed system, we can write here that beta is equal to S. So we're going to apply the Reynolds transport theorem to entropy. So beta is equal to S, and beta per unit mass. So S per unit mass is lowercase s. So that's our convention for going from extensive to intensive properties. The extensive properties are typically uppercase, typically, not always, and the intensive equivalent, which is the property divided by mass, is lowercase. We did all this stuff in the first couple of weeks of class, okay? So my beta now is going to be equal to S. And my lowercase b is specific entropy, or entropy per unit mass. And I end up with the closed system, open system entropy balance. ds dt for the closed system is equal to ds dt for my control volume, my open system, plus the sum of m dot s over all outlets minus the sum of m dot s over all inlets. Now, what is the change of S over time within my closed system? What's the change? What's the rate of change of S within my closed system over time? Well, that's equal to ds closed system dt, which is all this stuff. We have the entropy transfer due to heat, and we have S dot gen. So I can replace the left-hand side of this equation. So this is equal to sum Q dot over T interaction plus S dot gen. And that's from the closed system entropy balance. Closed system entropy balance. Okay, I'm going to do a little bit of algebraic manipulation here. Not much, just a little. I'm going to take this S dot gen and put it over on the right-hand side of the equation. And I'm going to get the following. the sum of the entropy generation, the entropy transfer due to heat interactions, Q dot over T interaction, is equal to the rate of change of entropy within my control volume plus the sum of the outflow of entropy from my control volume minus the sum of the inflow of entropy into my control volume minus, going to take the S dot gen and put it over on the right-hand side of the equation, S dot gen. Okay, so all I'm doing is taking the S dot gen term and putting it over on the right-hand side. All right, ladies and gentlemen, let's put a little box around this equation right here. Let's put a box around this equation. This is your open system. Entropy balance. Open system entropy balance. So let's go over each one of these terms here. Let's go over each one of these terms. The left-hand term represents entropy transfer due to heat interactions into control volume. So S transfer into a system, or open system if you like, into open system. Let me draw a little diagram here. So we have a device with a bunch of ports. I'm not going to draw them all. Bunch of ports. Make sure this looks right. Yes. Bunch of inlet and outlet ports. So we have an open system. This open system experiences various kinds of heat transfers at various interaction temperatures. So we have a Q dot, another Q dot. We have an interaction temperature for that Q dot and an interaction temperature for that Q dot. So we have various heat transfers, therefore transferring entropy into the system. We have various mass flows going into the system. So we have an M dot with some specific entropy, M dot with some specific entropy flowing into the system. And then we have various mass flows out of the system. Okay? And inside we have, so our system is an open system now. So here's our control volume. So inside I have a certain rate of change of entropy within my control volume. And I also have entropy being generated in the control volume. So I also have an S dot gen due to irreversibility within the system. Okay? So that's a multiple inlet, multiple outlet, multiple heat transfer device. So this device here, this open flow device, can receive entropy in the form of heat transfer divided by the interaction temperature. And then we got the rate of change of entropy inside my open system. Rate of S change in open system. And then we've got the, if you like, net outflow
of S due to mass flow. And then we've got the term that involves the entropy generation. S generated inside control volume. Or if you like, open system. Okay? Open system. So that's what all those terms represent in the open system entropy balance. Why don't we take a minute to play with this equation a little bit and see whether its behavior makes any sense. See whether its behavior makes any sense. We'll just do a few little examples here. So let's say we have a channel here that's insulated. So we have a channel here, or a pipe if you like, and it's insulated, so there's no heat transfer. So we have a m dot coming in, and we have an S at the inlet, and we have an m dot coming out, and a specific entropy at the outlet. Let's apply the entropy balance to this problem. Oh, one more thing. Let's assume this is a steady state. Steady state, steady state, steady flow. So nothing's changing in time. Nothing's changing in time. So let's see how the entropy balance here applies to our problem. So we got no heat transfer. So there's a 0 on the left-hand side of the equation. So I get a 0 equals. Okay, let's move to the next term. Change in entropy with respect to time within the open system. My open system is the channel or pipe. So let me actually put the system down here. I guess I should be careful here. So here's my system, my control volume, my open system or control volume. Steady state. So that means that the amount of entropy within my pipe or channel is constant in time. The entropy inside my open system is not going up and it's not going down. So it's constant in time. There's no buildup of entropy within the channel or pipe over time. So this term is gone as well. So I've got a 0. So I've got a 0 here. I can write explicitly ds within my control volume dt. So the change in entropy inside the control volume is 0. It's a steady state problem, okay? Now I've got one inlet and one outlet. So the summations go away and I simply have an m dot out, s out, and an m dot s in. So the summations go away because I have a single inlet, single outlet, and I have a plus m dot s out minus m dot s in. Okay, so that's what happens to the mass interactions there. And then I've got, okay, I have some entropy generation, possibly. I haven't said that this is a reversible device. I haven't said anything about entropy generation here. Maybe it's working irreversibly. Who knows? Maybe there's some friction going on in here. Or maybe there's some electric work going on that I don't know about. Who knows? Who knows? I don't have any wires in here, but you know, we shall see. So it's possible we have an entropy generation going on. So I'm going to leave that term there, okay? Now I'm going to take the S dot gen term and put it over on the left-hand side of the equation and group together my mass flow terms. S dot gen equals m dot. If we apply the mass balance to this thing, m dot out is equal to just m dot in, which is just equal to an m dot. If I apply mass conservation to the single inlet, single outlet, steady state, so dmCV dt is 0, okay? So I can factor out the m dot, and I get S out minus S in. So this tells me that the rate of entropy generation within the control volume is equal to the difference in specific entropy, or the change in specific entropy as the fluid enters and leaves the control volume, times the mass flow rate. If S out is greater than S in, entropy had to have been generated inside of the control volume, and the rate of entropy generation is the mass flow times delta S from the outlet to the inlet, okay? If S out is greater than S in, we had to have generated entropy inside the channel. So this equation gives us S dot gen if it exists or being generated within the control volume, okay? So that's what the entropy balance for an open system tells us, that if we have an adiabatic device, steady state, single inlet, single outlet, that the rate of entropy generation inside is delta S times m dot. That's what it's basically telling us. Where delta S is S out minus S in. Okay? Let's do another problem. Let's say we have a closed system. And this closed system is insulated. Here's my closed system. It's insulated. It's closed, so there's no mass interactions going on. Okay? Q dot equals 0. Insulated, okay? Let's apply the entropy balance to my closed system here, my closed system, and let's see what we get. Let's apply the open system entropy balance to my closed system. Well, there's no heat transfer going on, so this term is 0 because it's adiabatic. So I'm going to get 0. It's adiabatic or insulated. So that term is 0. I don't know anything about the rate of change of entropy within the control volume. By the way, my control volume or system is my closed system in this case. So I'm going to write ds Cv dt. I don't know what it is, but I can't get rid of it. ds Cv dt, the time rate of change of entropy within my system. ds Cv dt, the time rate of change of entropy within my system. It's a closed system, so I got no mass interactions. These terms go away. So I get a +0 and a -0. There's no mass interactions going on, so that goes away. And then I have my negative S dot gen term, the rate of entropy generated within the control volume or system due to irreversibility. So I also have an S dot gen. All right, so what I'm going to do here is I'm going to take the S dot gen and put it over on the left-hand side of the equation, and I'm going to flip the whole equation. I get the time rate of change within my system is equal to S dot gen. If entropy is going up in my system over time, it must be because entropy is being generated due to some sort of irreversibility in here. If there's no irreversibilities, S dot gen is 0 and entropy is fixed over time in my closed system. Okay? By the way, these open system conservation equations, whether it's the energy balance or the entropy balance or the mass balance, can be applied to closed systems. They're general. The mass terms go away and you're back to the rate-based closed system balances, okay? So these are just two examples here, very simple examples, applications of the open system entropy balance. In this case, we applied it to a closed system. You still get the right answer. So I hope this makes the open system entropy balance plausible, makes it plausible. Okay, I hope this makes the open system entropy balance plausible. Let's take a break here for a second and we will do an example involving the open system entropy balance. All right, let's do an open system problem here. We have a nozzle. So a nozzle is used for accelerating the flow. So we have a nozzle. Here's our nozzle system. So we have air flowing in on the left at state 1, and we have air exiting at state 2 on the right. So it's a steady state, steady flow air nozzle. The inlet temperature here, 350 degrees. Inlet pressure, 280 kPa, and the inlet velocity is 50 meters per second. So we have inlet temperature, pressure, and velocity at location 1. The outlet is at location 2, and pressure has fallen from 280 to 85 kPa, and velocity has gone up from 50 meters per second to 320 meters per second. So the inlet is at 50 meters per second, the outlet is at 320 meters per second, and that's accomplished by converting pressure power into kinetic energy. So you see a fall in pressure from 280 kPa down to 85 kPa at the outlet of the nozzle. Now, a couple of other details here. This is not an adiabatic nozzle. In fact, there is a certain amount of heat transfer. The heat transfer out, and I guess I better explain what the symbol means. The heat transfer out is the rate of heat transfer out divided by the mass flow of the air. So the air comes in at about 350 degrees. It leaves at some other temperature. So the air already comes in kind of warm, kind of hot. And as a result, the nozzle's kind of hot. So presumably, if the environment around it, it is at a lower temperature, we have some heat transfer from the hot nozzle system to the environment, provided the environment is cooler than the nozzle. So we have some heat transfer, Q out, which is Q dot out divided by the mass flow of the air of 3.2 kilojoules per kilogram of mass flow. So we have some heat transfer out of the nozzle because we're dealing with hot air flowing in and then out of the nozzle. The interaction temperature at the surface of the nozzle where the heat transfer occurs is given at 320 degrees Kelvin. That's the interaction temperature for the heat transfer from the nozzle. And the environment which surrounds the nozzle. The environment, everything outside of the nozzle, is taken to be at 293 degrees Kelvin. So this heat is being transferred from the hot nozzle to the cool environment, and the environmental temperature is at 293 degrees Kelvin. So in other words, well, we'll talk about this later. We'll talk about the environment in a minute, but let's focus on the nozzle. What are we supposed to find? We're supposed to find the outlet temperature, T2, of the air as it's accelerated through the nozzle. So we want to find the outlet temperature, T2. We don't know it. I want to find the entropy generation
per mass flow, per unit mass flow. So there's some entropy generation going on here. I want to find the entropy generated, rate of entropy generated per unit mass flow. So lowercase s gen. This s dot gen over m dot air will have units of entropy per unit mass. So that's why this is a lowercase s. Okay? No dot, lowercase s. So I want to find the outlet temperature, the rate of entropy generation per unit mass flow, S gen. And I also want to find out the rate of entropy transfer into the environment from the nozzle per unit mass flow. So I want to find out S dot environment divided by m dot air. I want to find the rate of change of entropy within the environment per unit mass of airflow. So I'm also interested in S dot for the environment. Because we have heat flowing from the nozzle into the environment, it's going to be carrying entropy with it. So I want to know what the rate of change of entropy within the environment is, or the entropy transfer into the environment due to the heat interaction with the nozzle. Okay, that's what I'm interested in. Okay, let's get started here. Let's find the outlet temperature, T2. By the way, I'm going to assume something here. I'm going to assume ideal gas behavior for the air. Presumably, the temperatures look fairly healthy and the pressures look fairly low. Provided the outlet temperature isn't close to zero, I think we're pretty good shape, assuming ideal gas behavior. Okay, so let's find the outlet temperature, T2. So analysis. So let's write the energy balance here. Why am I going to write the energy balance? Because if I can find an outlet specific enthalpy, if I can find an H at state 2, I can go to an IGB table and find T at state 2. So let me apply the entropy balance. So T2 is actually equal to T evaluated at H2, which I don't know, but maybe I can find it using the energy balance. Okay, so E balance. This is an open system, by the way. We have a single inlet, single outlet. So this is definitely an open system. So we're going to be using our open system energy balance. So what? I have Q dot minus W dot, and there could be multiple heat transfers going on, is equal to dE/CV dt plus, and then I've got the sum of m dot H plus PE plus KE summed over all outlets minus the same thing summed over all inlets. Okay, so there's the energy balance for my nozzle. Now it's a steady state problem, so this is zero. Steady state, we're given the steady state nozzle. I don't see any non-pressure work going on here. I don't see any wires. I don't see a propeller in here. I don't see that the nozzle itself is deforming in terms of shape and size, so there's no boundary work going on. So I can immediately get rid of this work term here. So that's gone. Let's also attack the potential and kinetic energy terms here, at least the potential terms. I don't see any overall change in height of the air, and even if there was an overall change in height, the density of the air, rho, is so small compared to any conceivable height change for the inlet and the outlet. I think we can neglect changes in potential energy from the inlet to the outlet. So I'm going to get rid of these potential energy terms right here. I'm going to write this down in my assumption. Delta PE from the inlet to the outlet is 0. Okay, I'm just going to write that. By the way, if we were dealing with something like water and there was a major height change, maybe we were dealing with a dam where the height change is perhaps 100 meters, and it was water with a density of 1,000 kilograms per cubic meter, you might have a significant change in potential energy, but this is air. Air has a density of about 1 kilogram per cubic meter, and I don't see any indication in the diagram that these have any height change whatsoever in this problem. So potential energy terms are gone. I have a single inlet, single outlet, so the summations go away, and I simply have m dot h plus ke at the outlet. The outlet is at location 2, and I also have m dot h plus ke at the inlet, okay, which is location 1. I'm not going to do the mass balance on this thing. If you apply the mass balance, you'll find that m dot in is equal to m dot out, or m dot 1 is equal to m dot 2. So I'm just calling m dot 1 and 2 m dot because they're all the same. Okay, let's see what I got. Q dot, oh, heat interaction. I got one heat interaction. So I got one heat interaction. I guess I'm just calling it Q dot. I got one heat interaction and it's out. So it's actually out. So I'm putting a negative sign right there. It's out. I can either put a negative sign in the numerical value, or I can put, what's the best way? I guess I'll leave the negative. I'll put it in the numerical value. That way we're not getting confused here. So I got Q dot is equal to m dot, and then I think I'm going to group together terms here. M dot H2 minus H1 plus KE2 minus KE1. Okay, so there's my energy balance here. Now I don't have Q dot or M dot. All I have is Q dot per unit mass, Q dot out over M dot. I guess I could have put negative Q dot out there. That might have been the way to go. Maybe I'll go over and do that. So this is actually Q dot out. Out. I'll call it Q dot out. I guess I'm using a subscript here. Yeah, there we go. Out. Out. Okay, that looks good. So I think I will make the substitution in the energy balance. So I don't know Q dot or M dot, but I do know everything on a per unit mass basis. So, so let me change this to negative Q dot out. Negative Q dot out. So I'm going to divide by M dot and solve for H2. So let me divide by M dot and solve for H2. So let's see here. I'm going to put everything else but the H2 term, and I'm going to put it over on the other side of the equation, and I'm going to flip the whole equation. So I'm going to have H2 equals H1 plus, and then I've got KE1 minus KE2, and then I have the negative Q dot out divided by M dot, which, by the way, is Q dot Q out. Q dot out over M dot is Q out. So my final equation here, we have H2. Let me expand what these kinetic energy terms are, specific kinetic energy. So I have H1 plus. So each of these is going to be a 1/2 velocity squared. So I'm going to factor out the 1/2. And I have velocity at the inlet minus velocity at the outlet, both squared. And then I have negative Q out. Okay? Now, I know these velocities, VL velocity 1 and 2. I know the heat transfer out. H1, I don't quite know what H1 is, but I do know the inlet temperature.
let's see here, H1 is equal to H evaluated at T inlet, or T1, and the inlet temperature is 350 degrees Kelvin, as I recall. So yeah, 350 degrees Kelvin, looks good. So 350. And I can look up the specific enthalpy for air in a table, 350 degrees. Let's see here. Screen share. So here's my IGB table, 350 degrees. Looks like specific enthalpy is 350.49. 350.49. So we'll put that up. 354.49. Okay, so that's from tables. Let's see here. So that means, let me plug in some numbers here. So we have 350.49, and then I have plus, let's keep the unit here. Let's be careful with the unit. Kilojoule per kilogram plus 1/2 the inlet velocity. Inlet velocity is 50 meters per second. The inlet velocity is 50 meters per second, and the outlet velocity is going to be higher at 320 meters per second. It's a nozzle. So 50 and 320. So we have 50 meters per second squared minus 320 meters per second squared. And then I have minus q dot out, which is q dot out per m dot, sorry about that. Lowercase q out, which is 3.2 kilojoules per kilogram. 3.2 kilojoules per kilogram. Now, one little thing is here, we need to be careful about the units on this equation. These terms are both in kilojoules per kilogram, but the kinetic energy terms are going to be in joules. Once you square the velocity, you get meters squared per second squared, which is a joule per kilogram, not a kilojoule. So we got to be really careful here. In fact, I'm going to put this in a moment. I'm going to convert from joules to kilojoules. So there's 1 kilojoule per 1,000 joules. So that'll take care of that term. And then I get my minus 3.2 kilojoule per kilogram for my heat transfer. Okay? And so we get an outlet specific enthalpy of 297.34. 297.34. You got the 1/2 there too. 297.34. 297.34. Or if you like, 0.3 kilojoule per kilogram. Okay, so the outlet enthalpy, H2, 297.3 kilojoule per kilogram. That means the outlet temperature is about 297 degrees. So T2 is equal to T evaluated at H2, which is 297.3. And if you go to a table, that's about 297.3 degrees Kelvin, okay? So I'm going to put a little box around this guy. There's our outlet temperature, T2. So we got the outlet temperature, T2 now, okay? Outlet temperature is T2. Okay, so the air comes in pretty hot at 350 degrees K and leaves at about 300 degrees K. Just shy of 300 degrees K. All right? That looks good. Let's find the entropy generation per unit mass flow that occurs inside our nozzle. Entropy is being generated, maybe, we'll see. We'll see if entropy is being generated. Let's calculate how much entropy is generated inside our nozzle per unit mass flow. That's lowercase s gen. So how are we going to do that? Let's apply the entropy balance. Let's apply the entropy balance to my control volume, my open system. Okay, our nozzle. So S balance. This nozzle is an open system, so I need to write the open system S balance. What? The sum of Q dot over T interaction equals the time rate of change in S within my control volume plus the sum of M dot S out minus the sum of M dot S in minus S dot generated within my control volume, i.e. the nozzle, okay? Now this is a steady state problem, so immediately I can get rid of this. Steady state, so that's gone. I have a single inlet, single outlet device. So I got one outlet and one inlet, so this is M dot S2, and this is M dot S1. The inlet is at location 1 and the outlet is at location 2. Inlet location 1, outlet location 2. So my mass flow terms reduced to one of each. How many heat interactions do I have? I have one. I have one heat interaction. One heat interaction, and I'm given an interaction temperature. I've got an interaction temperature. In fact, it's 320 degrees, and I have a heat transfer per unit mass out of my control volume, my nozzle. So I have a heat interaction, and I got one. So this summation goes away, and I have a single heat interaction, Q dot, I'll put a negative Q dot out over T interaction. Okay, negative Q dot out over T interaction. It's an outflow of entropy due to a heat interaction. Okay? So let's solve S dot gen. So I'll take the S dot gen, I'll stick it over on the other side of the equation. I'll take the heat transfer term and stick it over on the right-hand side of the equation, and I will have S dot gen, the rate of entropy generation inside my nozzle. Rate of entropy generation inside my nozzle. So I have Q dot out over the interaction temperature. And now I'm going to group together these terms. They involve an M dot, so I'll have M dot S out minus S in. The negative sign went away on the Q dot term because I put it on the right-hand side of the equation and it became positive. So what is this telling me in words? This tells me in words that the rate of entropy generation is equal to the difference in outflow versus inflow entropy plus the outflow of entropy due to the heat interaction. That's what this equation is saying, okay? If entropy is flowing out, let's say there was no mass flow at all. Let's say this term was gone. No mass flow, that means the rate of entropy generation is equal to the rate of entropy transfer out of the system due to the heat interaction. That makes sense. That makes sense. Okay, now this Q, okay, so we need to massage this a little bit more. Let's divide everything by M dot. So I got S dot gen over M dot equals Q dot out over M dot, and that's divided by the interaction temperature. And then I got plus S out minus S in. So I'm dividing everything by M dot. The S dot gen divided by M dot is my lowercase S gen, or entropy generation per unit mass flow. And my Q dot out over M dot is my heat transfer per unit mass flow. So this becomes my Q out. So I get S gen, lowercase, S gen is equal to Q out over the interaction temperature plus S out minus S in. Or if you like, remember here, the outlet is at location 1. Sorry about that. Outlet is at location 2. And the inlet is at location 1. I guess I'm getting back to my old notation here. I thought I got rid of this. Outlet is 2. Inlet is 1. Outlet is 2. Inlet is 1. There we go. Okay? Now I have the outlet heat transfer, the heat transfer out, and I also have the interaction temperature. The interaction temperature, as we just said a moment ago, was 320 degrees. So I got my heat transfer per unit mass out, and then I've got the interaction temperature, 320 degrees. So I've got this first term. I've got this. I need to get the entropy change from the inlet to the outlet. So I need this thing. I need this delta S from 1 to 2. That's what I need. Now, how do I get it? Well, I can use one of the property relationships. So prop relationship for IGB delta S from 1 to 2. Okay, now I got to be careful here. Is this a constant or a variable heat problem? If it's a constant specific heat, then I can write Cp ln T2 over T1 minus R ln P2 over P1. I could do that. I'm sorry, yeah, minus R ln P2 over P1. Or if it's variable specific heat, I have to use the S naught stuff. S naught 2 minus S naught 1 minus R ln P2 over P1. This problem doesn't say anything about constant specific heats. This problem doesn't say anything anywhere about constant specific heats. So that means I need to get the actual entropy generation, not the approximate entropy generation. So I need to use the S naught stuff, variable specific heat. So let me write down the property relationship involving the S naughts, i.e. variable specific heat. So we have S naught evaluated at T2 minus S naught evaluated at T1 minus R ln P2 over P1. Okay, so that's our property relationship for entropy, IGB, variable specific heat. IGB, variable specific heat. I guess I'm putting the naught. I always get this mixed up. I guess I'm putting the naught in the superscript. Okay, that matches the notation in the text, in the notes, okay? Okay, let's crank some of this stuff out here. Tell you what, I'm going to erase this. Well, I guess we'll leave it. First of all, let's find S naught at T1. S naught evaluated at T1, which is 350 degrees Kelvin. Not a lot of room here. Let's see, I go to property tables, IGB air property tables, and let's see if we can pull out an S naught here at the inlet temperature. 350, here's 350. Here's S naught. 1.857 kilojoule per kilogram degree in Kelvin. 1.857 kilojoule per kilogram degree in Kelvin. Let's find S naught at the outlet, which is actually S naught evaluated at the enthalpy. H2 is 297.3. Probably have to do a little bit of interpolation here. Sorry, I should have stopped scaring the screen. So we got S naught at state 1, which was at 350 degrees. S naught at state 2. So S naught at state 2 is S naught evaluated at a specific enthalpy of 297. That's what we calculated from the energy balance. Might have to do a little bit of interpolation here. 297. Let's see if we can pull out a specific S naught here. So let's look up So 297 is between these two data points right here. So that means S naught is going to be between these two data points right here. It looks to me like it's closer to the 1.7. Closer to the 1.7. I do an interpolation and I get 1.692. 1.692 kilojoule per kilogram to green Kelvin. 1.692 kilojoule per kilogram degree in Kelvin. Okay? So that's interpolation. Interpolation. So I'll write here. Interpolate. Oh, I guess, do I need to turn off my screen? I do need to turn off my screen again. So interpolated S naught to 1.6692, and that's interpolated from IGB air table, okay? Okay, so I've got these S naughts. I also have the pressures at the inlet and the outlet. So let's see here. I get, give myself a little bit more room. I get 1.692 minus 1.857, and these all have units of kilojoules per kilogram, degree in Kelvin. And then I get R for air, what? 0.287 kilojoule per kilogram, degree in Kelvin. And then I have natural log. And what's pressure P2 over P1? Let's see, P2, 85, P1, 280 kPa. 85 and 280 kPa, running out of space here. 85 and 280 kPa, the units cancel out. And this will all have units of kilojoules per kilogram, giving me a delta S here. Let's see if I have a delta S. 1.177 kilojoule per kilogram degree in Kelvin, 1.77. 1 equals 1.77 kilojoule per kilogram degree in Kelvin. So this delta S, I now know, 1.77 kilojoule per kilogram degree in Kelvin. Let's see, oops, I'm sorry, I got this wrong, I'm sorry. 0.177. Sorry about that. That seemed a little high. That's a lot of entropy transfer. 0.177 kilojoule per kilogram degree in Kelvin. Sorry about that. So we now know delta S from 1 to 2. Okay, I'm running out of room here. I'm just going to immediately switch up to the top here, rewrite my equation for S gen, and we're going to crank out what S gen is. So lowercase, S gen, which is S dot generated per unit mass flow. So that's Q out over the interaction temperature plus delta S from 1 to 2. We have everything now. Let me get rid of this, same equation. And I get, Q out. Q out. 3.2 kilojoules per kilogram, and the interaction temperature is 320 degrees. That's how hot it is, where the heat's being transferred at the outside of my nozzle. So 3.2 kilojoule per kilogram. And then that's being divided by 320 degrees Kelvin. And then I got plus delta S from 1 to 2. So that's 0.177 kilojoules per kilogram degree in Kelvin. All the units are the same. That looks good. And so I have, let's crank this out here, 3.2 divided by 320 plus, this is about 0.01 plus 0.177, and I get 0.187 kilojoule per kilogram degree in Kelvin. So the rate of entropy generation per unit mass flow, S-gen, which is the rate of entropy generation inside my nozzle, S dot gen per unit mass flow of air through my nozzle, is 0.187 kilojoule per kilogram degree in Kelvin. Question, is this nozzle reversible or irreversible? It is irreversible. S dot gen is greater than 0. So note, greater than 0, irreversible nozzle. Irreversible. So there's some friction going on in there. There's some unconstrained expansion. We got a pressure drop. We got a pressure drop across the nozzle. So we got a pressure drop, high pressure, low pressure. Maybe the pressure isn't dropping reversibly. Maybe there's some weird fluid dynamics going on inside, some flow separation. All sorts of stuff can be going on. There's mainly friction in there, probably a lot of friction in there. And that's resulting, so friction is the air molecules rub up against the sides of the nozzle. The metal, if it's made out of metal, it'll rub up against the side. Or the air molecules rubbing up against each other as they change velocity. So there's probably a lot of friction in there, and that's resulting in entropy generation. There may be some irreversible heat transfer as well. There may be some irreversible heat transfer. The heat transfer is probably pretty complicated inside of there. Liable, there's some irreversible heat transfer, okay? So this is an irreversible nozzle because we have entropy generation inside. Okay, so now let me draw this picture one more time. Let me go over here and redraw my schematic. Some stuff cleaned up here. So inside my nozzle, I have an S dot. I have an S-gen. I'm going to put a number in here now, 0.187, and that's kilojoule per kilogram degree in Kelvin. So I got some entropy being generated in there per unit mass flow, okay? Now I want to know what's the entropy transfer? What's the entropy transfer into the environment? So this nozzle sits in a room, it sits in a facility. That's called the environment, whatever is outside of the nozzle sufficiently far away. So let's calculate the entropy transfer into the environment due to the operation of the nozzle. Let's calculate the entropy transfer into the environment. Let's calculate the entropy transfer into the environment. So here's our environment right here. Here's the nozzle. It's way over here. And so some heat is being transferred, Q out, which is equal to Q dot out for M dot. We have some heat being transferred from the nozzle to the environment, okay? So this is the environment. Now, I tell you that this environment is at a temperature. I give the environmental temperature. Let's go back and look at it here. So I give the environmental temperature as 293 degrees Kelvin. So that is the temperature of the environment. T of the environment is 293 degrees Kelvin. Now, the way I'm drawing the environment, everything in the environment has a temperature 293 degrees Kelvin. I'm telling you, that is the environmental temperature. What that means is, if I put a thermometer on the edge of the environment, it's still 293. So I put a thermometer right there, measure the temperature, the interaction temperature. The interaction temperature for the environment is also equal to the environmental temperature. I'm telling you that the environment has a temperature, the whole thing, including on the boundary. So let's calculate let's apply the entropy balance to the environment and figure out what the change in entropy is of the environment. Let's figure out what the change in entropy in the environment due to the heat interaction from the nozzle. So let's apply our entropy balance to the environment. So this is going to be my system, the environment. Apply S balance to environment. Now, the first question to be asked is, what version of the entropy balance? Open closed system, rate-based, process-based, overall process, what? Well, the first thing, the environment is actually a closed system. We have heat transfer, but this is not a mass transfer, it's heat transfer. The amount of mass in the environment is constant. It's just a separate entity way far away that is receiving the heat from the nozzle. So the environment is a closed system. The nozzle is an open system. So I'm going to write the closed system entropy balance. Let's see here. Q dot over T interaction plus S dot gen is equal, I guess I'll write it the right way, ds dt for my closed system, which is the environment, is equal to the sum of Q dot over T interaction for the environment plus S dot gen for the environment. Environment, 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 okay? First of all, we only have one source of heat, and that's going to be equal to Q dot out from the nozzle, and then I have an interaction temperature for the environment. I know the interaction temperature, I know the heat transfer per unit mass, so basically I know these terms more or less. I don't know Q dot, but I do know Q dot per unit mass. I do know Q dot per unit mass, okay? Now, if the surface temperature, if the temperature of the environment is uniform, at the boundary, inside, anywhere in the environment is 293 degrees, then we have no heat transfer inside the environment due to temperature differences. Everything is the same temperature in the environment. So we don't have any irreversible heat transfer inside the environment. Presumably, we don't have any friction in the environment or any unrestrained expansion. I don't have any information. The point is, I'm going to assume that there are no irreversibilities occurring in the environment. I have no information. I have no information. So I'm going to make a big assumption here that S gen in the environment is 0. Or if you like, S dot gen in the environment is 0. The temperature is uniform in the environment. The temperature is uniform in the environment. I don't have the information about any weird pressure drops or any frictional processes. I got no information. Okay? So I think it's a pretty good assumption that we're going to neglect any irreversibility associated with the running of the nozzle in the environment. I got no information. I'm really interested in what's happening because of the nozzle. That's really what I'm interested in. What's happening to the environment due to the presence of the nozzle? Okay, so this tells me that the rate of change in the environment of entropy, so this says ds environment dt is equal to q dot out over the environmental interaction temperature, which is the environmental temperature. The interaction temperature is equal to the environmental temperature for the environment. Basically, the definition of an environment is uniform temperature. That's the point. So on the boundary, it's the environmental temperature. In the interior, it's the environmental temperature. It's the same thing everywhere. Okay, now, I am going to divide left and right-hand side of this equation by m dot for the air going through the nozzle. I'll associate the m dot with the q dot out term, and I'll associate the m dot with the d environment, ds environment dt, and this becomes the change in entropy per unit mass flow in the environment. So this is called S environment, or actually, I guess I'll keep my notation how I did it in the introduction here. This will be S dot environment over m dot of air in through the nozzle. Okay, I think I'll write it like that. And this whole thing becomes q dot out over m dot divided by the interaction temperature, which is q out over the environmental temperature is the interaction temperature. Okay? So let me write the final equation that I have. The time rate of change of entropy within the environment per unit mass flow through the nozzle is Q out over the environmental temperature. I have Q out, it's 3.2 kilojoule per kilogram. And the environmental temperature, what's the environmental temperature? 293 degrees. 293 degrees. (293 Kelvin, and I get a final rate of entropy transfer into the entropy change of the environment per unit mass flow. Let's see, 3.2 divided by 293, and I get 0.011 kilojoule per kilogram degree in Kelvin. So kilojoules per kilogram of airflow per degree in Kelvin. So this environment here is gaining entropy So S dot over, this is for the environment, over M dot airflow through the nozzle is 0.011 kilojoule per kilogram degree in Kelvin. So that's due to the entropy being transferred from the nozzle to the environment. Okay. Let's also calculate, so we've got this now. Let me write this result down. Let's investigate this. We just cranked some numbers out. Let's investigate what's going on. So let me write right over here. S dot environment over M dot for the air is equal to 0.011 kilojoule per kilogram degree in Kelvin. So let's put a little box around there, all right? So this guy, S dot environment per mass flow of air through the nozzle is equal to 0.011 kilojoule per kilogram degree in Kelvin, okay? Okay, so that's a change in the environment. Let's calculate the total change in entropy of the universe. Let's calculate the total change in entropy of the universe here. S dot universe over M dot for the air. Let's calculate the rate of entropy change, the rate of entropy change in the universe. Let's calculate that. Well, the rate of entropy change in the universe is equal to the entropy generated per unit mass flow in the nozzle. So we have S dot gen over M dot, and this is for the nozzle. So the entropy generation inside of my nozzle. Okay, so that's going to increase the entropy of the universe. Plus what? Let us look at the entropy transfer right here at the surface of the nozzle. Let's actually calculate the flow of entropy, not at the environment, which we've already done, but let's calculate the entropy flow right here. S flow at nozzle boundary. Let's do that. Let's calculate the S flow right at the nozzle boundary. The flow of entropy at the nozzle boundary is equal to Q dot out over the interaction temperature, or per unit mass flow, Q out over the interaction temperature. Let's calculate that. Let's calculate, and that's the interaction temperature for the nozzle. Let's see, 3.2 kilojoule per kilogram, and the nozzle interaction temperature is 320 degrees. 320 degrees. 3.2 kilojoule per kilogram degree in Kelvin, and 320 degrees Kelvin. The, kilojoule per kilogram. So 3.2 divided by 320. 3.2 divided by 320. 0.01 kilojoule per kilogram degree in Kelvin. So right here, entropy is leaving at a rate of 0.01 kilojoule per kilogram degree in Kelvin, right at the surface of my nozzle. But it's entering the environment at 0.011 kilojoule per kilogram degree in Kelvin. So the amount of entropy flowing into the environment is greater than the entropy flowing out of the nozzle. What is going on? Let me draw this one more time. So here we have our nozzle. And it's transferring heat to the environment. I know the transfer of entropy at the surface of my nozzle is 0.01 kilojoule per kilogram degree in Kelvin. And I know the transfer of entropy into my environment is 0.1011. Kilojoule per kilogram degree in Kelvin. So entropy increased as the heat flowed from the nozzle boundary to my environment. Why? What is going on? So the temperature here, the interaction temperature is 320, and the interaction temperature right here is 293 degrees Kelvin. So 320 and 293. Heat is flowing from hot to cold. 320 to 293. Heat's flowing from the hot nozzle exterior to the relatively cool environmental boundary and then into the environment. Is that a reversible or an irreversible process? It is irreversible. We have heat transfer, Q dot out. Q dot out from hot to cold across a finite temperature difference, 320 to 293. That is irreversible, therefore there's entropy being generated in this region. Entropy is being generated between the nozzle and the environment. Due to finite temperature difference. So let's calculate that S-gen in the region between the environment and the nozzle. So here we have my nozzle. Here we have the environment. So entropy is being transferred into this region by an amount 0.01 kilojoule per kilogram degree in Kelvin, and it's being transferred in to the environment at a rate of 0.011 kilojoule per kilogram degree in Kelvin. And in between is my buffer region, or my boundary between the two systems. So I got this buffer region right here. Buffer. Or if you like, transition. Transition region. Remember we talked about the transition region? We talked about where entropy is generated in systems. And between systems, we got this buffer region. What's S dot gen in this buffer region? What's S dot gen in this buffer region? Well, let's apply the entropy balance to the buffer region. Let's see here. ds dt for my transition or buffer region, trans, is equal to the sum of the heat transfers over the interaction temperature plus S dot gen in my transition region. This is a steady state problem, so this term goes away. There's no entropy building up in my transition region, so what flows in and what is generated must have to flow out. I have two entropy transfers. I have 0.01 minus 0.011 kilojoule per kilogram degree in Kelvin. I have two heat interactions going on. Here's the entropy flows from the nozzle and into the environment. What comes in from the nozzle is being added. What flows out to the environment is being subtracted. Okay? So this gives me S dot generated in the transition region is equal to 0.011 minus 0.01 kilojoule per kilogram degree in Kelvin, or if you like, 0.001 kilojoule per kilogram degree in Kelvin. That's my, oh, sorry. Got to be a little careful here, getting a little sloppy. I'm going to divide, if I divide this by m dot, so here we go. Forgot to divide by m dot. Divide the entire right-hand side by m dot. The s dot gen becomes an s dot gen over m dot, and the q dot becomes a q dot over m dot, or a little q, okay? Forgot to divide by m dot there. So S dot generated per unit mass flow of air through the nozzle is equal to, give myself a bit more space here, 0.001 kilojoule per kilogram degree in Kelvin. Okay, so this has been a long elaboration, but I think this is worth looking at. The change in entropy of the universe is the sum of all the entropy generated due to irreversibilities. So I've got entropy being generated in the nozzle. I got no entropy being generated in the environment because it's reversible heat transfer. The environment is at the environmental temperature, so there's no S-gen in here. But I also have this buffer or transition region as the heat flows from the nozzle to the surrounding environment. There's a thin buffer region over which temperature falls from 320 to 293. There's a small or a large buffer region, and that's where the entropy is being generated. So now I've got this plus S dot gen over m dot, and this is for the transition. And so let me add up everything. Let's see here, S dot gen, S dot gen for the nozzle is 0.187 kilojoule per kilogram degree in Kelvin, plus the entropy generated in the buffer or transition region, 0.001 kilojoule per degree Kelvin, and that gives me 0.188 kilojoule per kilogram degree in Kelvin. So the entropy change of the universe, which is the sum of the entropy generation for all processes involving this nozzle, S dot universe over M dot is 0. I'm not going to write this here. S dot universe over M dot is 0.188 kilojoule per kilogram degree in Kelvin. This is a nice little result. This shows us that the device overall contributes to increasing the entropy of the universe by 0.188 kilojoule per kilogram degree in Kelvin. Or if you like, kilojoule per degree Kelvin per kilogram of mass flow rate through the nozzle. Okay? So that's the entropy change of the universe. All right, ladies and gentlemen, I think that's long enough. And I will talk to you later.